Around 720 BC, the 10 tribes of the Kingdom of Israel disappeared from the record of history. They were forced to move to the northeast and never came back to their homeland. This exile is supported by Assyrian records, the Bible, and archaeological discoveries. But none of these historical sources clearly tells us where these people finally went. Not only their physical destination, but also the genetic path of their descendants stayed a mystery. Where are the descendants of those about 27,000 people who were exiled so long ago? For nearly 2,500 years, this question mostly remained in the world of legend. British colonialists claimed they knew the answer. Traditions in Afghanistan also said that certain communities were descendants of the Israelites. And in Ethiopia, some communities built their own religious identities around similar claims. But modern genetics has tested many of these claims using real DNA evidence. As a result, most of these claims lost their credibility. Yet one community stood out. Its haplogroup data matched, its genetic proportions were consistent, and even its geographic spread followed a pattern expected from a forced migration that happened 2,700 years ago. In other words, the lost tribes of Israel may never have truly disappeared. Their DNA simply kept moving quietly through history. To understand why this genetic discovery matters, we first need to understand what really happened thousands of years ago and how scientists can trace its effects across 2,700 years. The historical record of this exile is surprisingly clear. Two separate sources confirm almost the same event. Assyrian records, written on clay tablets in cuneiform, describe the conquest of Samaria, the capital of the northern kingdom of Israel. They record the deportation of thousands of people by the Assyrian king Sargon II. The Hebrew Bible also records this event, especially in 2 Kings chapter 17. It names places such as Halah, Habor, and the cities of the Medes. These were real places. Halah is usually linked to a region in northern Iraq. Habor refers to the Kabur River Valley in northeastern Syria, while the cities of the Medes were in what is now northwestern Iran. The exiled people were not simply sent into the desert to die. They were purposely resettled across the Assyrian Empire as workers and population support. The Assyrian policy was highly organized. People from conquered lands were removed and scattered across the empire, while people from other regions were brought in to live on their old lands. This plan was made to stop strong local identities from growing and to lower the chance of future rebellion. Written records strongly confirm this process, but there is something those records cannot tell us. What happened to those thousands of people and their descendants in the centuries that followed? Keeping detailed population records requires administrators, stable institutions, and political continuity. The Assyrian Empire collapsed in 612 BC, less than a century after these deportations. The bureaucracy that had tracked these populations disappeared along with the empire. From that point on, the displaced communities had to survive on their own. There was no longer an empire recording their movements or carrying out official population counts. This is where genetics becomes powerful. DNA does not need an administrative system to preserve history. It carries its own record. Human populations collect mutations over time at measurable rates. When populations become separated, their DNA begins to follow different evolutionary paths. The longer they stay separated, the more genetic differences build up. By tracking specific genetic markers, researchers can estimate how long two populations have been separated and even estimate the size of their ancestral populations. One of the main tools used in this kind of research is the haplogroup. A haplogroup is a group of genetic variations passed down through certain family lines, either through the Y-chromosome or mitochondrial DNA. You can think of a haplogroup as a kind of genetic family tree. It can tell you which ancient family line you belong to. Haplogroups can also be traced across geography and history. From the Neolithic period through the Iron Age, populations living in what is now Israel, Lebanon, Jordan, and western Syria, the ancient Levant, have been strongly linked to haplogroup J1. Within J1, one subtype, J1c3, has been reported at important frequencies among some ancient Israelite and Jewish remains. Another important marker is haplogroup J2, which is also found strongly among populations of the Levant. These were the genetic fingerprints researchers were searching for. The question was simple: which modern populations keep a large share of ancestry linked to ancient Levantine populations? The goal was not just to find signs of occasional contact or regional interaction. Researchers wanted patterns that matched ancient migration and long-term population continuity. To answer this question, scientists first needed a baseline. They needed to know what the genetic profile of ancient northern Israelites might have looked like before the forced migrations. But without a time machine, directly sampling DNA from 2,700 years ago is difficult. So geneticists turned their attention to a community that had stayed in the region since ancient times. These were the Samaritans, who kept living around Mount Gerizim and held on to their distinct religious traditions. The Assyrians deported thousands of people, but they did not remove the entire population of the northern kingdom. Poor farming workers who were useful to the empire were left behind. Modern Samaritans trace their ancestry to some of these people, especially groups linked to Ephraim and Manasseh. Most importantly, their community kept strict marriage practices for centuries. As a result, their gene pool stayed relatively separate from outside populations, almost like a genetic time capsule. When researchers studied their DNA, they found something remarkable. The Y-chromosome lineages of Samaritan men were dominated by haplogroups J1 and J2. This gave researchers a living genetic baseline for comparison. With this ancient genetic fingerprint as a reference point, scientists could begin tracing the descendants of the exiled populations. The first target was the region deep in the Middle East that had once been part of the Assyrian world. Specifically, researchers studied communities in present-day Kurdistan, where ancient place names such as Hala and Habor had been linked to the Assyrian deportations. For centuries, a distinct community known as Kurdish Jews lived in this region. They spoke dialects that preserved parts of ancient Aramaic and kept a strong Israelite identity. Starting in the late 1990s, geneticists collected DNA samples from men in these communities. They compared them carefully with the genetic baseline taken from Samaritans near Mount Gerizim. The results were striking. Among Kurdish Jewish men, haplogroup J1c3, matching a lineage found among Samaritans, appeared at important frequencies. This suggested a possible connection to populations that had been moved into the region during the Assyrian period. Using molecular clock methods based on the buildup of genetic mutations, researchers estimated when certain Samaritan and Kurdish Jewish lineages split. The estimated time was very close to the period of the Assyrian conquest of Samaria, around 722 BC. The evidence suggested that at least some of the populations linked to the lost tribes had not simply vanished from history. But the genetic investigation did not stop there. Researchers next turned their attention south, toward the Arabian Peninsula. In Yemen, a Jewish community had existed for centuries in an isolated and difficult environment. Could they also preserve ancestry connected to the lost tribes? Again, researchers used the Samaritan population as a genetic baseline. They compared newly available Yemeni Jewish DNA data with that reference. The result was striking. Men from the Yemeni Jewish population also carried J1c3 at important frequencies. Two communities far apart from each other, separated by language and culture, seemed to share deep ancestral connections to populations of the ancient Levant. This was a historical connection that written records could never fully preserve. The displaced populations had not necessarily disappeared. They may simply have moved beyond the places where historians could still track them. But how could populations move from Kurdistan to Yemen without losing their genetic identity? The answer may lie in the rise and fall of the great empires that ruled the Middle East after Assyria. In 539 BC, Cyrus the Great and the Persian Empire conquered the Neo-Babylonian Empire. The Achaemenid Persian Empire created a huge political network stretching from India to Egypt. This vast political space created safer trade routes and wide communication networks. Descendants of populations displaced by the Assyrians could use these imperial networks to move south in search of economic opportunities. One important route crossed the Arabian Peninsula and connected different parts of the ancient world. But movement alone does not explain how genetic signatures survived. One of the most important reasons may have been endogamy, strict marriage within the community. These communities could adopt local languages, clothing, and cultural practices while keeping strong boundaries around marriage and ancestry. Cultural assimilation and genetic assimilation are not always the same thing. Another genetic marker often discussed in this context is the Cohen Modal Haplotype, or CMH. The idea is that certain paternal genetic traits can be passed from father to son across many generations. In 1992, an international research team collected DNA samples from men who identified with priestly Jewish families around the world. Their communities looked very different and had different cultures, from Ashkenazi Jews to Sephardi and Middle Eastern Jewish populations. Yet DNA analysis showed that a large share of them shared a distinct genetic signature. This signature was linked to a particular branch of the J1 lineage. This finding gave genetic support to the idea of a shared ancient paternal ancestry among some priestly Jewish lineages. And this discovery would later lead researchers far beyond the Middle East, to southern Africa. In southern Africa lives a black ethnic group known as the Lemba. For generations, they have kept traditions claiming that their ancestors came from the north and were connected to Jewish people. They traditionally avoided certain foods, practiced circumcision, and used symbols that looked like the Star of David. For a long time, these traditions were dismissed as legends or as the result of later Christian influence. But in 1999, researchers studied the DNA of Lemba men. They found a remarkable result. A genetic signature linked to the Cohen Modal Haplotype appeared among Lemba men, especially within certain priestly lineages. In some groups, the frequency was reported to be unusually high compared with many Jewish populations. The question then became, how could such a population have reached southern Africa? Some groups moving south eventually turned toward the sea in search of new opportunities. Using seasonal monsoon winds, travelers could cross the Indian Ocean toward the East African coast. There, they interacted and married with local Bantu-speaking African populations. As a result, their mitochondrial DNA, passed down through the maternal line, became overwhelmingly African. But the paternal Y-chromosome lineages could preserve traces of the earlier ancestry. Lemba traditions also speak of a mysterious city called Senna. From Samaria to Kurdistan, from Yemen to southern Africa, the genetic story suggests an extraordinary journey. It shows the remarkable power of human survival and religious tradition. But while some groups traveled south, others moved east. They entered the deeper parts of Asia along the Silk Road. Their journey followed one of the most famous trade networks in human history. Under the protection of the Persian Empire, merchants and travelers moved into unfamiliar parts of Asia. Their routes stretched beyond modern Iran toward the mountainous regions of Afghanistan. Some Pashtun tribes have traditionally called themselves Bene Israel, meaning children of Israel. Their tribal traditions and Pashtunwali customs have sometimes been compared with parts of ancient Jewish law. Practices involving circumcision and limits on certain foods have been pointed to as possible similarities. However, genetic research in this region has been extremely difficult because of modern conflicts. Limited samples have found some markers suggesting connections with populations of the Middle East. But unlike the Lemba case, a clear concentration of a priestly genetic signature has not been firmly established. The search for stronger evidence therefore moved farther east toward India. On India's western coast lives a community known as the Bene Israel. According to their traditions, their ancestors arrived after a shipwreck and consisted of 7 couples. For centuries, they seemed deeply integrated into Hindu society. Yet they kept strict endogamous marriage practices. When their DNA was studied, researchers again looked for the presence of the Cohen Modal Haplotype and other paternal markers. Farther east, near India's border with Myanmar, another community exists, the Bene Menashe, who identify themselves as descendants of Manasseh. They have East Asian physical features but keep traditions including the Sabbath and customs they connect with ancient Israel. Their oral traditions describe a journey from the Assyrian exile through Persia and China before finally reaching northeastern India. Claims that were once dismissed as myths or coincidence became new pieces of a historical puzzle when viewed through the lens of population genetics. In the 21st century, these genetic discoveries also created important discussions in modern Israel. Israeli religious and political authorities studied genetic evidence and traditional claims about communities such as the Lemba and certain Indian groups. As a result, some members of these communities eventually made Aliyah, returning to Israel after thousands of years. The people who were chained and driven from their homeland by Assyrian armies did not simply disappear. They spread across the world. Their skin color changed. Their languages changed. Their cultures changed. Yet traces of ancestral DNA may have remained. The lost tribes were not necessarily erased from history. They may have become part of the extraordinary diversity of populations around the world. Thousands of years passed. Empires collapsed. Languages disappeared. Stone walls wore away and turned back to dust. But the human body preserved an invisible historical record. Across African savannas, Afghan mountains, Indian coasts, and the mountains of Myanmar, traditions and modern science began to meet. Together, they suggest a powerful story about the survival of displaced peoples. People forced from their homeland became seeds scattered across the world. Even in difficult conditions, they planted new roots and survived. The mystery that began with the fall of Samaria was now being lit up by genetics. The story of the lost tribes leaves us with one important lesson. History is not just something that happened in the distant past. It can still remain written in the ancestry of people living today. Thank you for watching. If you enjoyed this journey through history, please consider subscribing. History may be closer to us than we think. See you in the next story. In 2022, a team of population geneticists published a study that caused a quiet shock in the scientific community. They collected DNA samples from more than 15,000 people across the Arabian Peninsula, the Levant, North Africa, and the Iranian Plateau. They compared haplogroup frequencies, studied genetic mixing models, and calculated genetic distance scores between major Arab and Persian populations. When the results were mapped geographically, one finding stood out so strongly that the researchers repeated the analysis several times to make sure it was correct. The result challenged many of the stories these two civilizations had told about their identities for centuries. In the next part, we move beyond the Middle East and examine ancient DNA evidence suggesting the existence of populations whose descendants can no longer be clearly identified. This is another strange and fascinating chapter of human history. This story is about two populations that have developed distinct identities over more than 1,400 years, Arabs and Persians. They speak different languages, have different ethnic identities, and hold different historical narratives. Yet DNA analysis makes the story even more complicated. To understand why, we first need to understand what scientists are actually measuring. DNA does not recognize nationality. It does not care about religion, language, or which empire your ancestors served. DNA carries genetic lineages known as haplogroups. Y-chromosome haplogroups trace paternal lines, while mitochondrial haplogroups trace maternal lines. When two populations share the same haplogroups at important frequencies, it can suggest that they had common ancestors at some point in the past. The important question is how far back those common ancestors lived. And this is where the story becomes complicated. Sharing a haplogroup does not mean that two populations are the same people. It only suggests that they were connected at some point in their history. Researchers also use a method called genetic admixture analysis. It studies a person's genome and estimates ancestral parts that came from different ancient populations. Think of it like a recipe. Your DNA might contain 40% ancestry from one ancient population, 35% from another, and 25% from a third. By modeling thousands of individuals, scientists can rebuild invisible migration histories that helped shape modern populations. In the Middle East, these migrations go much farther back than the Arab and Persian empires. They reveal the stories of people whose names were never written in history books. The research first created a baseline for understanding what Arab DNA actually looks like. But there was an immediate problem. There is no single genetic profile that can be called Arab DNA. The word Arab mainly describes a linguistic and cultural identity rather than one single genetic population. And when researchers studied Arab populations, they found remarkable internal diversity. For example, Arabs from Syria, Lebanon, Jordan, and Palestine show strong genetic connections to ancient populations of the Fertile Crescent. Haplogroup J2 can appear at important frequencies among Levantine populations. Haplogroup E1b1b is also present and reflects ancient movements between North-East Africa and the Levant. Haplogroup J1 is also common in several Arab populations. Gulf Arab populations are different again. Populations from Saudi Arabia, the United Arab Emirates, Kuwait, and Qatar can show high frequencies of haplogroup J1. This lineage is strongly linked to ancient populations of the Arabian Peninsula. It is especially common among populations connected with ancient Semitic-speaking groups and pre-Islamic Arabian tribes. This is the genetic profile many people imagine when they hear the phrase Arab DNA. But even Gulf Arab populations are genetically complex. Their genomes contain ancestry from several different regions. Yemeni Arabs also have distinct genetic features. They preserve some of the oldest genetic lineages found on the Arabian Peninsula. They also carry important East African ancestry, showing thousands of years of sea contact across the Red Sea and Indian Ocean. Haplogroup E1b1b appears at notable frequencies among some Yemeni populations. North African Arab populations, especially Egyptians and Moroccans, contain a large amount of North African and Berber-related ancestry. Iraqi Arabs hold something like a middle position. Their ancestry includes genetic components inherited from ancient Mesopotamian populations that existed thousands of years before the Arab and Persian civilizations. All of this shows that Arab DNA does not come from one single origin. It is highly diverse. The same is true on the Persian side. Modern Persians living in central and northwestern Iran preserve a very ancient genetic profile. Haplogroup J2 appears at important frequencies, similar to some Levantine Arab populations. Another important marker is haplogroup R1a, linked to ancient population movements from the Eurasian steppe. These movements are connected with the spread of Indo-Iranian languages. R1a is much less common among many Arab populations. Among Kurdish populations, R1a can appear at even higher frequencies. This reflects their distinct historical and geographical origins. Azeris in northwestern Iran also show ancestry connected with Turkic-speaking populations from Central Asia. Meanwhile, Baloch populations in southeastern Iran have genetic components linked to South Asian populations and the ancient Indus region. Iran is therefore a genetic mosaic made up of many different ancestral parts. But when researchers compared the genomes of Persian populations with Gulf Arab populations, an unexpected pattern appeared. The genetic distance between Central Persian populations and Gulf Arabs was smaller than the genetic distance between Gulf Arabs and Yemeni Arabs. In other words, populations that define themselves as Arab can sometimes be genetically more distant from each other than they are from Persian populations. To understand why, we must go much farther back in time, before Arabs, Persians, empires, or modern religions existed. There we meet a population known as the Natufians. The Natufians lived in the Levant about 15,000 to 11,500 years ago. They were hunter-gatherers who started settling in permanent communities earlier than many other populations. They were among the earliest people to build fairly settled communities and gather wild grains before agriculture was fully developed. Remarkably, genetic signals linked to the Natufians can still be detected among both modern Arab and Persian populations. Natufian-related ancestry is especially important among populations of the Levant. Different Arabian populations carry different amounts of this ancestry. Modern Persian populations also keep a strong ancestral component connected to ancient peoples of the Fertile Crescent. This means Arabs and Persians both inherited part of the genetic legacy of ancient populations that settled the region thousands of years ago. As early farming populations expanded, their ancestry moved east into the Iranian plateau. It also spread south toward the Arabian Peninsula, mixing with populations already living there. This represents one of the deepest shared ancestral connections between Arab and Persian populations. No one living in Tehran or Riyadh necessarily thinks of themselves as a descendant of Natufian hunter-gatherers. But genetically, traces of these ancient populations remain. There is another invisible ancestral component, Ancient North Eurasian Ancestry, or ANE. Ancient North Eurasians lived across parts of northern Eurasia during the Ice Age. Because they left relatively few direct descendants, their existence is mainly known through ancient DNA. Yet their genetic signal appears across huge geographical distances. This ancestry entered the Middle East through large-scale migrations linked to the Eurasian steppe and the spread of Indo-European languages. Modern Persian populations preserve measurable levels of this ancestry. Arab populations generally carry lower levels. Some of this ancestry likely entered through historical contact between northern Arabia, Iran, and steppe populations. The difference is important. The amount of ancient North Eurasian ancestry helps show the effect of ancient migrations from the steppe. Around 4,000 years ago, Indo-Iranian-speaking populations brought extra ancestry into the Iranian plateau. Arabian populations farther south were less affected by these migrations because of geography. As a result, there are measurable genetic differences between Arab and Persian populations in this particular ancestral component. Yet, their overall genetic distance remains smaller than many people might expect from their cultural and political histories. One huge migration helps explain why. It was the spread of farming populations during the Neolithic period. Thousands of years ago, farming populations from the Fertile Crescent spread in many directions, north into Europe, east into Central Asia and the Iranian plateau, and south toward the Arabian Peninsula. They were not armies, they were family groups moving in search of fertile land and resources. Yet they changed the genetic landscape of the whole region. They left shared ancestral signals that can still be seen among Arab and Persian populations today. This shared Neolithic ancestry forms an invisible connection between two civilizations that have often described themselves as fundamentally different. But when we turn to the Arab conquest, the story takes an unexpected turn. The genetic data reveal one of the most surprising findings. In 636 AD, Arab forces defeated the Persian Empire at the Battle of Al-Qadisiyah. Within only a few decades, one of the greatest empires of the ancient world collapsed. Persia was absorbed into the growing Islamic Caliphate. Arabic became an important language of religion, administration, and political power, while many Persian elites converted to Islam. If we looked only at the political history, we might expect this conquest to have left a huge genetic impact. But it did not. Genetic data show that Arab-related ancestry among modern Persian populations remains relatively limited. Despite one of the most important conquests in human history, the genetic impact was surprisingly small. A military and cultural transformation that changed religion, language, writing, and political identity left relatively little genetic evidence in the Persian population. The Persian genome survived the Arab conquest largely intact. Why? The answer lies in the scale and direction of migration. The Arab forces that conquered Persia were mainly soldiers, not large groups of settlers. The Caliphate needed local administrators, tax collectors, scholars, and political leaders to rule its enormous territories. Persian bureaucrats, scholars, and elites were too valuable to simply remove. Many adopted Islam and Arabic administrative practices while remaining in their homeland. Arab soldiers who settled in the conquered territories were concentrated in cities such as Baghdad and Kufa in what is now Iraq. There was no massive migration of Arab settlers deep into the Persian heartland. The study also looked at another subject that is rarely discussed publicly, the genetic legacy of the slave trade. For centuries, the Persian Gulf was an important center in Indian Ocean slave trading networks. Enslaved people from East Africa were brought to both Arabian and Persian ports. They were absorbed into households, military units, and eventually broader civilian populations. Their genetic signals can still be detected today. By tracking certain mitochondrial haplogroups and genome-wide ancestry components, researchers can identify East African ancestry among Gulf Arab populations and coastal Iranian populations. The higher levels on the Arabian side reflect the scale and length of the slave trade in the Gulf region. This ancestry is rarely discussed in public conversations about Gulf identity, yet it remains present in the DNA of people who may not personally identify as being of African descent. The genome records facts that historical documents sometimes leave out. But this raises another question. If Arab and Persian populations are genetically more similar than their modern identities might suggest, why have their identities stayed so clearly separate? The answer may be that genetic similarity was never the true foundation of either identity. Arab identity developed around language, tribal ties, and Islam. Persian identity, meanwhile, developed around imperial traditions, a rich literary heritage, and a special connection to its pre-Islamic past that survived the conversion to Islam. Both identities are cultural constructions rooted in real historical experiences. Neither needs biological distinctiveness to have meaning. But the genetic data challenged nationalist stories that portray these two populations as fundamentally different biological groups. The political differences between the Arab world and Iran, and between Sunni and Shia political blocs, are real and can have serious consequences. But they are ultimately political, historical, and religious divisions. They are not written into the genome. What the genome reveals is a much older and deeper shared history. Today, there are roughly 450 million Arabs across more than 20 countries and around 85 million Iranians. Many people carry narratives that stress deep differences between these populations. Yet the DNA of Gulf Arabs and the DNA of Persians from places such as Isfahan both carry echoes of the same ancient Natufian heritage. It is the legacy of ancient people who built some of the earliest villages in the Levant around 12,000 years ago. Their descendants still carry genetic signals inherited from populations that helped make agriculture and settled civilization possible. And that is where our journey ends, for now.